In our assignments with differential equations, you'll soon see that there are just a few different types of problems that we face quite often. This is one of them. Can we show that this differential equation satisfies a given function? So let's find the derivative of this function, x prime. If we're differentiating with respect to t as our independent variable, the derivative of sine is cosine of the glob times the chain rule on the glob. So of course we would probably immediately put that in front of that function. And then let's go find the second derivative. So differentiating again, the 2 would be in front of the derivative. The derivative of cosine would be negative sine. And then again we would have another chain rule. So you could put these together. So our x double prime would look like negative 4 sine of 2t. And then let's look at what we can do here. We can see that this sine of 2t appears before. So the sine of 2t we can replace. So we would have x double prime is equal to negative 4x. And rewriting that, we have verified these two equations. Whoops, kind of missed there with my arrow. These two equations are the same. So we verified that one is a solution of that differential equation. Let's do the same idea here with this next problem, this dy dx is a derivative. So to show that that's equal to 4x, we could do some work here with both sides, and we could differentiate dy dx here, and we've got 4x. So that would be another way to do a little bit of work with both, but you're verifying that one leads to the other is all there really is to it. Find a solution of this differential equation. We actually know this is a polynomial or a power term, so we actually know how to do the antiderivative. So if this is y prime, then we know that we would simply raise the exponent to 3 and divide by it, and then we would add a constant. So remember, this was called a general solution to the differential equation, and we happen to know an initial condition. So our initial condition here says that when x is 2, we get 13 for y. So we can solve for the value of c. And now we know a particular solution or a specific solution. So we go from that family of antiderivatives to one specific solution if you know the initial condition. All right. In number 4, we have a vertical motion problem, and we're given an initial velocity here of 24 feet per second. Our first question is, what is the differential equation that's involved here? Well, the thing that we know is acting upon this ball that's thrown vertically in the air is the acceleration due to gravity. So for part A, what we know is that the acceleration function is the same as the position function, which you could use s for position or height. I guess here the problem asks us to use y of t since it's a vertical motion problem. So we are actually given the acceleration due to gravity. Remember, when we're measuring in feet per second, that you're going to use negative 32 feet per second. All right, so once we know that acceleration function, then we can back up to y prime, which we actually know will become our velocity function. So this would be a negative 32t plus a constant, but here we can give a better name to that constant since we know that this is our velocity function. So we know that this constant is the initial velocity. So we already know that that was given in the problem to be 24. So now we've got our velocity function, which is our y prime of t. So we can replace that initial velocity with 24. And, I guess I should be more careful to answer the question here. The initial condition. So for part B, the initial condition is the V sub 0 is 24. Question C then, we can keep going here to answer how high the ball rises. We could answer that from our velocity function because we know that it reaches the maximum height when v of t is equal to 0. So we could continue and find the position function, but for this question we need not do that. So our velocity will be equal to 0 when 32t is equal to 24. So 24 over 32 would be 3/4, and this would be a time in seconds. So now what remains is how high does the ball rise? So that would require us to actually find the position function. So we're going to take our velocity function here and do one more antiderivative. So we were asked to call it y of t in this case. So our position function, we would raise that exponent to a 2 and divide by it. So we'd have negative 16t squared plus 24t. Plus our initial height. So our initial height, in this case, we're told that it was from ground level. So we know that this initial height, y sub 0, is 0. So we're almost ready to go here then. So let me scroll to get some space. So now we know our position function, negative 16t squared plus 24t. And we found out that it reaches its maximum height at 3/4 of a second. So you could grab your calculator to do this arithmetic, or it's not going to be so difficult if you do some canceling. We will come up with 9 feet as the maximum height. All right, so not much motion there. And in question 5, the population of a community in hundreds at time t measured in years is given by this exponential function. So if the population is 600 at time 0, so there's our initial population. So remember that P sub 0 is our constant C in these models. Think about what happens. Well, let's make sure that's clear to everyone here. Let's take our function and look what happens if t is equal to 0. If we put 0 in for t, do you see that we get e to the 0 power, which becomes 1? So that's why we know the initial population is the constant c. So now we have our function more specifically, not a general function, but a specific exponential function. And now it says to use the function to find the population after 3 years. So we simply want to substitute 3 in for the variable t. So you could grab your calculator and round this off. And I think I have 6.971 hundredths. So you could certainly multiply by 100 and then add more decimal places. So that would also be okay if you said 697.101. So either of those answers would be acceptable. When will the population reach 1500? This is a more interesting use of this function. So now we want to know when is the dependent variable going to reach a certain population. So we take our formula or our model, and this time we want to substitute for the population and solve for the exponent. So you know to solve for an exponent this will involve logs, but first let's simplify. Let's divide both sides by 600, And 15 over 6, I guess we could write as 5/2, or 2.5, does not matter. You can use your calculator for these problems. If you didn't have a calculator, your next step is to take the natural log of both sides, because that allows us to bring the exponent in front. And of course, you don't have to write this natural log of e, that would become a 1. So our exact value for t would be the natural log of 5/2 divided by 0.05 or 1/20th, however you want to write this. So this is 1/20th. So perhaps if you were going to leave your answer in exact form, and you can also say the log of a quotient is the difference of two logs, but that doesn't serve too much purpose. I better add units here though. So there's our exact answer. And let me scroll back up so you remember that our unit for time was in years. So we could leave this as our exact answer, or we could grab a calculator, and I have 18.326 years approximately, if I calculated that correctly. And that should take care of the assignment.